Hey guys, hope you're all doing good. In the last two videos, you would have hopefully learned how to perform steady state simulations at different valve lifts. Now, one of the reasons why we asked you to do that is this is a common practice that is followed by a lot of companies that actually run analysis on valves. So at different valve lifts, the pressure drop that occurs through your valve is going to change. Now, if you have the value of pressure loss at different valve lifts, then you can actually calculate the valve flow coefficient. This flow coefficient data is extremely useful because it helps you compare one valve against the other valve. Not only that, having this flow coefficient curve can help you make your zero-dimensional or one-dimensional valve models more accurate. So that being said, we are going to jump to the second phase of this problem where we are going to be running a transient simulation. So one of the powers of using computational fluid dynamics is you can basically look at the valve dynamics as the inlet pressure is changing, because that is one of the characteristics of a proportional valve, because the inlet pressure is going to change as a function of time, and engineers would be interested in looking at how the valve actually opens for a given value of pressure. Now, in order to do this perfectly, you would have to resolve all of your pressure waves so that you get your valve dynamics very accurately. And unfortunately, if we do that, then our simulation time is going to be extremely huge. However, I will actually show you how engineers in companies set up their simulation if they are interested in capturing detailed valve dynamics. So to get started, the first thing we need to do is we need to go to run parameters, and we need to make sure that this is no longer a steady solver. We are going to use transient solver because we are going to be varying inputs as a function of time. Let's click on OK and then yes. So once we have done that, I'm going to click on simulation parameters and I'm going to enable body force, and then click on body force and then go to Z direction and enable gravity by putting in a value of -9.81. Okay, so the primary change comes to our inlet boundaries. So if you go to inlet boundary, you can see that currently we have a single pressure which is 30 bar. I'm going to click on use file. And what I'm going to do is I'm going to provide a temporal profile, meaning I'm going to vary the pressure as a function of time. So what we have done is we have already created an Excel sheet that basically contains time and the pressure that's going to act on the inflow. So I'm going to copy this data, and this Excel file is shared with you, so you should also be able to do it. I'm going to come here, right click, and I'm going to paste rows. So when you do this, I will have my pressure as a function of time. Now remember, pressure should be in pascals. So if you are using pressures in bar, you need to multiply that by 1 E5 or 1 followed by 5 zeros. I'm just going to call this as inlet pressure.in. And you can also click on this graph button to understand how the pressure variation is going to be. You can see that initially the pressure is very high, and this is going to push open the valve at least a little bit. And once it reaches a maximum value, the pressure is quickly going to drop. So this means our valve is also going to drop to its initial state as it experiences gradually lowering pressures. So let's close this guy and accept the pressure and click on OK. Now in terms of geometry, what you want to do is you want to basically bring the valve down to its original lift. So in this case, let's go to transform, translate, selected boundary, and we are going to move it in the opposite direction by 2 mm. So that means the current lift is going to be 1 millimeter. So this should be the starting point for this particular study. The next thing that I want to do is click on physical models, and I want to enable the fluid structure interaction model. Click on apply and click done. Then go to boundary, and I'm going to click on valve spindle, and I'm going to say that this is going to be a wall boundary, but it's going to be an FSI object. So this way we know that this boundary is going to be moved based upon fluid structure interaction. That is, at each and every time step, Converge is going to calculate the pressure forces that are acting on the valve spindle. It's going to integrate the pressure to calculate Fx, Fy and Fz. Then we basically have an equations of motion solver that moves the spindle accordingly. So let's click on OK. And then we are going to go to the physical models where we select fluid structure interaction. The first thing that you need to do is you need to create an FSI object. So once you create an FSI object, you add a boundary to it. So in this particular case, it's going to be our valve spindle. Then we come to parameters. Now in this particular case, we would like the FSI calculation to begin right away. So the start time is minus 9E5 or minus 9E6. Don't change that, because this way we know for sure that FSI is going to begin right from the first time step. So then we have to set up the center of mass. In this particular case, we are going to compute the center of mass using the geometric center. Okay. And we are going to specify the mass value, which I believe in this particular case is 3.1 kg. Okay, so once you have done that, what you can do is you can set up initial velocity or initial rotation and along with the initial rotation axis, but none of those inputs are required for our problem. So you can directly go to forces and moments. So here there is something called as a constant applied force. Now we would need to apply a constant force in the negative z direction. So that is really important. Remember, the spindle has a particular preloading, right, which is about 7,126 newtons. That needs to act in the negative z direction. So make sure that you put in minus 7126 here. Okay, and then there is another option called as 1 DOF, which is called as 1 degree of freedom. So we want our spindle to move along the z axis. So I'm going to say that it is constrained to move only along the z direction. So there is no rotation for sure, and translation along x and y direction are also prohibited, which means out of the 6 available degrees of freedom, 5 are constrained. So you have only 1 DOF or 1 degree of freedom, and that is a translating degree of freedom along the z axis. So the direction is going to be 1. Now there is something called as minimum displacement and maximum displacement, correct? So we don't want to change the value of minimum displacement, but we do want to change the value of maximum displacement. So what does that mean? To demonstrate that, I'm just going to click on OK here, and I'm just going to come here. Okay, so here as the pressure forces are going to act on the spindle, it's going to push open the valve, correct? This valve spindle is going to move up, and in that process, this particular boundary or this particular layer of triangles is going to get compressed. Now if the valve lift is too much, if it is greater than this particular length, then it can actually cause problems. So let me demonstrate that by translating the spindle along the z-axis by 10 centimeters, which is nothing but 0.1 meters. So if I click on apply and if I run diagnosis, you can see that that's basically the limit. If I do undo here and if I push open the valve by 12 centimeters and click on apply, you can see that it has clearly intersected with the geometry. And if you hit find, you will see that there are problems. So we need to make sure that the spindle doesn't move away by 10. So we need to make sure that the spindle does not move more than 10 centimeters. So let me click on find again, no errors. So go to case setup, go to FSI, parameters, 1 DOF in max displacement. Remember this is in meters, so I'm going to put in 0.1 meters, which is 10 centimeters. And let's click on OK. We are not going to hit that limit, but if we do hit that limit, the displacement of the spindle would be stopped so that the case does not crash. And we will be able to capture all of this when we do the post-processing. Now, one important thing that we need to change is our simulation parameter. Now, if you go to boundary, inlet, you see that up to 1.5 seconds you're simulating the entire event. So you might want to run the simulation for maybe 1.6 seconds. The initial time step is 1e minus 9. The minimum time step is 1e minus 9 as well, and max time step is 1 second. Click on OK. And then we go to output files. We want to make sure that we are resolving this event. So, we are running the simulation for about 1.5 seconds, right? We would at least want to, get like 100 pictures of this entire event. So I will say that 0.015 is basically my time interval for writing 3D output files. I hope that makes sense. And I want data to be written every 1e minus 9 seconds. So pretty much every time step we will definitely have an output file. And restarting can also be done a bit more carefully because there is a chance that the simulation might crash. So maybe we will write restart files every 5 milliseconds, but we are going to keep only 3 restart files. So let's click on OK now, and that basically concludes our transient case setup. So I'm going to export this case setup and I'm going to run the simulation. Once I have the results, I'll come back again and discuss that. With that, I would like to conclude this video and I'll see you guys in the next one. Bye.